Hello, everyone. Welcome to FirstOnlineUniversity, a global platform for all your education and growth related needs. In this lecture, we are going to continue with the chapter Aldehydes, Ketones, and Carboxylic acids. And we will study in particular about the isomerism that is seen in aldehydes and ketones. Before we begin, a piece of information for you. You can use the coupon codes Mission JEE or Mission NEET while you enroll at First Online University for Mission JEE or NEET. Let us start with part 1 of isomerism in aldehydes and ketones. Now, we have already seen that there are different types of isomerism that exist, can be structural or stereoisomerism. When we talk about structural, we have different types like chain isomerism, where the aldehydes, like we have seen chain isomerism, linkage, ionization, hydration, so on and so forth. So when we talk about specifically aldehydes and ketones, we will be discussing each of these isomerisms in detail. The first one that we are going to talk about is chain isomerism. Now, when I say chain isomerism, what do we mean by it? Now, chain isomerism refers to the isomerism that exists in aldehydes which have 4 or more carbon atoms and ketones with 5 or more carbon atoms that show chain isomerism. For example, if we have, say, C4H8O, that's the molecular formula that is given to us, what are the possible compounds that we can form? We can form butanol, or we can also have the formation of 2-methylpropanol. So here the length of the chain is different because of a branching that is appearing in the second isomer that has been shown. Since they differ in the length of the chain, we call them as chain isomers. Secondly, if we have the formula C5H10O, we can have pentanol possible, or we can also have the possibility of 2-methylbutanol. Another possibility is 3-methylbutanol. Another possibility is 2,2-dimethylpropanol. So if you see for a molecular formula C5H10O, there are 4 different isomers that can exist, which are having different chain lengths. And since they differ in the length of the chain that these compounds have, we call them as chain isomers. And they are known to exhibit chain isomerism. Third example of the same compound C5H10O, we can talk in terms of ketones. So we can have pentane-2-on, we can have pentane-3-on, we can also have 3-methylbutane-2-on, right? So when I say that even in case of ketones, these 2 different isomers will exist, which will have the same molecular formula but different structural formula. And since the structural formula or the structure is differing in a way that they have different chain lengths, these are going to be examples of chain isomers. Next, we can have C6H12O. So here we can have the possibility of hexane-2-on. We can have the possibility of 3-methylpentane-2-on. We can also have the possibility of 4-methylpentane-2-on. So when we see that 3 different isomers are existing, see, whenever I put forward the molecular formula in front of you, that is C6H12O, try to write down the possible isomers by yourself before you actually proceed forward in the video. You can pause the video at that time, form the isomers by yourself, and then you can recheck. This is how you will have a practice of forming the isomers by yourself, okay? And you will also learn in the process. That will increase your speed of doing such questions. So here again, since they have different chain lengths, hexane has 6 carbon atoms in the parent chain, pentane has 5 carbon atoms in the chain, but since we have different positions of the substituent methyl, so we will also count all of them as chain isomers. So the question here for you is, chain isomers of C6H12O is, so that's what I was telling you, if you would have actually practiced, you would have been able to answer it. And we have seen that all, so hexane-2-on was yes, 2-methylpentane-2-on, 4-methylpentane-2-on, all of these were the isomers of this given molecular formula. So all of these is the right answer here. Next question is the chain isomer of this particular compound CH3, CH2, CH2, CHO. So since you can see, you have an the aldehyde group has to be the terminal group. So all you can do is put 1-methyl as a substituent. So that would be 2-methyl propanol or 3-methyl propanol, 2-methyl ethanol. So option A is going to be the right answer because 3-methyl propanol would just be equal to butanol only. 2-ethyl ethanol will be equal to butanol only. So that's just to confuse you. 2-methyl propanol is the right answer. That is option number A. Now we move on to the second type of isomerism that is seen in aldehydes and ketones, that is position isomerism. See, all the isomerism cannot be possible in all the functional groups. That is something which is important for you to know. We have already discussed the chain isomerism. Now we'll be talking about position isomerism. In chain isomerism, there was a difference in the length of the chain and also in the position and also in the the branching. Okay, the branching resulted in different chain isomers and position of that branch. But here, in case of position isomerism, the aliphatic aldehydes, first of all, are not going to exhibit position isomerism because position isomerism is basically the change in the position of the functional group itself. Okay, there was a change in the chain isomerism. We saw that there was a change in the position of the branch that was present in that particular compound. Here we will be talking about change in the position of the functional group itself. Now, since in case of aliphatic aldehydes, the CHO group will always be towards the end of the chain, or you can say towards the beginning of the chain, we can never have its position getting changed. So it will not exhibit position isomerism. So therefore, aromatic aldehydes are able to show position isomerism. For example, if we have 2-methyl benzaldehyde, or we call it as orthotolualdehyde, we can have it at methyl at the third position. We can have the methyl at the fourth position. That is meta and para isomers. So ortho, meta, para are going to be the three isomers which are called position isomers because we have the difference in the position of the functional group here. Now you will say, how is the position of the functional group varying? It's not the functional group, it's actually the methyl group that is varying. If you carefully see, with respect to the functional group, the methyl group is varying, but with respect to the methyl group, the functional group is varying, right? That is why we call it as position isomerism. The third type that is seen is metamerism. Now, metamerism is shown by higher ketones because there are two different alkyl groups which are attached to the same functional group, that is C double bond O. So if we have, you will understand through examples what is metamerism. So if we have the molecular formula C5H10O, we can have the formation of pentane 3-on, that is diethyl ketone. That is, if you look at the functional group, that is carbonyl carbon, that is carbonyl group, that is C double bond O. To one end of the carbonyl carbon, we have ethyl group, and to the other end we have ethyl group. So both are going to be the same. We can also have the possibility where on one end we will have the methyl group, on the other hand we will have the propyl group. So it's going to be methyl propyl ketone, or we call it as pentane 2-on. So when we have the variation in the the number of carbon atoms or the substituents on both the sides of the functional group, we call that as metamerism. So if the same polyvalent functional group is present in two or more organic compounds, then you have to write metamerism as compared to position isomerism. Okay, so position isomerism is going to be a change with respect to the position of the functional group, and metamerism will be changed with respect to the substituents that are present on both the ends of the functional group. The fourth type of isomerism that is seen in case of aldehydes and ketones is functional isomerism. Now, when we say functional isomerism, see, every isomerism is going to indicate by its name itself that what does it mean. All you need to do is to understand and remember a bit about what we are discussing here. Okay. So functional isomerism, when I say aldehydes and ketones, they show functional isomerism in them. In addition, they are also related to enols. What are enols? Enols. That means unsaturated alcohols, ethers, and other cyclic compounds. For example, if we have, say, C3H6O, we want to form the acyclic isomers. We can have propanol, we can have propanone, that is acetone. We can have prop 2-in-1-ol, or we can have methoxyethene. So if you see, there are 4 different functional groups that are present. So the functional isomerism is going to be exhibited by those compounds which have the possibility of the presence of different functional groups in different isomers. So I hope the functional isomerism is clear to you. If we look at the cyclic isomers of it, there can be a possibility of oxetane, there can be a possibility of 2-methyl-oxirane, and there can be a possibility of cyclopropanol. So we have seen the acyclic isomers also and cyclic isomers also. So a total of 7 isomers are possible for the given molecular formula. The next type of isomerism, which is very, very popular, very commonly used, and very, very important in case of aldehydes and ketones, especially um, especially important from the examination point of view, is tautomerism. Now, tautomerism is when you have the conversion of a ketone group or an aldehyde group, that is C double bond O to COH. Okay, so when we see the example of it, we'll be able to understand it better. So if we have the molecular formula C2H4O, okay, we can have the formation of acetaldehyde. Now, what will happen is that we can have this double bond or this pi bond shifting here and this hydrogen shifting here. So there is going to be a shift of hydrogen from here to here, forming OH here and a double bond here. This is the vinyl alcohol that is getting formed, and this type of isomerism is called tautomerism. Another example is C3H6O, where we have propane 2-on or acetone, and we can have the formation of prop-1-ene 2-ol. So I hope the transfer of hydrogen and the transfer of double bond is clear to you. The exact mechanism of tautomerism we have already discussed in the isomerism concept. You can go back and revise that. But here, all you need to remember is the shifting part, because see, you cannot just sit in the examination, revise the whole mechanism, write it down, and then see what the product is. You will have to somehow develop a mnemonic to understand as to where are you going to actually make it functional there. So for that, you need to remember what are the shifts that are going to take place. So hydrogen is getting shifted from the methyl group to the oxygen, and there is also a shift of the double bond. That is something you need to understand. Now, let us see a few concept check questions based on what we have learned in this lecture till now. The first question is, the aldehyde does not exhibit position isomerism. So, which of the following aldehydes will not exhibit position isomerism? Before I move on to giving you the options, you need to remind yourself of what is position isomerism. As is clear from the name, there is going to be a difference in the position of the functional group. Now, since we know that there is one specific type of aldehyde which will not be able to get its position shifted of the aldehyde group to some other position, is the alkyl. So that's aliphatic aldehydes, which will not be able to get the position of the aldehyde group shifted from one to another, because they are going to be always terminal aldehydes. So if we look at the option, I've already told you the answer. So option B obviously is the right answer. But if you look at formaldehyde, no, formaldehyde, you know, will not exhibit. There is no just space. Okay, there's just one carbon atom. Aromatic aldehydes, on the other hand, are capable of exhibiting position isomerism. So option B should also be the right answer. I think, okay, there is something wrong with the options that have been given. The D option is both B and C. Okay, both B and C. So then option D would be the right answer. I'm really sorry for this mistake, but you can understand. Okay, we've already studied this. The second question is, ketones show the property of allotropism, polymorphism, metamerism, or none of these. So allotropes are those for carbon. We have already seen the carbon allotropes. So allotropism, we know, is not something associated with ketones. It is associated with carbon. It's associated with inorganic chemistry. Again, polymorphism is a concept of inorganic. When we have different polymorphs of sulfur existing, okay, the rhombohedral and monoclinic, all these are polymorphs. We are not again getting into inorganic chemistry, but we know what is metamerism when there is going to be different functional groups, different substituents on both the ends of the functional group, that is on both the ends of the carbonyl carbon, that is going to be differing in the isomers. We call it as metamerism. Therefore, option C is going to be the right answer. This is all about the isomerism in case of aldehydes and ketones. You need to know what each isomerism means. That means you do not have to learn the definition, but the moment the word or the name of the isomerism comes in front of you, you should be able to quickly remind yourself of what that isomerism actually has in it. And you should also be very well versed with the examples of different isomerisms that we have seen. So do practice a lot of questions because that will make the concepts better. Better clear in your mind. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app through Google Play Store or App Store for continuous learning through your smartphones. Keep learning with First Online University, a team of millions of learners and educators worldwide.